For centuries, humanity believed the universe was far simpler than it truly is. Our understanding has repeatedly been transformed whenever new instruments allowed us to see farther, measure more precisely, and challenge assumptions that once seemed unquestionable. In the early 20th century, astronomers were still debating whether the Milky Way represented the entire universe or merely one galaxy among countless others. That picture changed dramatically when Edwin Hubble studied distant objects such as the Andromeda Galaxy and demonstrated that they were independent galaxies far beyond our own. His observations also revealed something even more profound: the universe itself is expanding. But determining exactly how old the universe is proved much more difficult. Early estimates produced a serious problem. Some calculations suggested that the universe could be younger than the oldest rocks found on Earth. Over the decades, observations of the cosmic microwave background, measurements of stars, and increasingly precise astronomical instruments gradually improved our estimate. Today, the age of the universe is generally placed at roughly 13.8 billion years. That number is almost impossible to comprehend. One way astronomers communicate this enormous timescale is through the cosmic calendar, an idea popularized by Carl Sagan. Imagine compressing the entire history of the universe into a single year. The Big Bang takes place at midnight on January 1st. Earth does not appear until late in the year. Human civilization arrives during the final moments of December 31st. Our entire recorded history occupies only a tiny fraction of the final seconds. And yet, within that microscopic period of cosmic time, humans developed telescopes capable of observing galaxies billions of light-years away. But the deeper we look, the more complicated the universe becomes. Consider the motion of stars inside galaxies. Stars located far from the centers of spiral galaxies often orbit at unexpectedly high speeds. If visible matter were the only source of gravity, those outer stars should behave differently. This observation became one of the major reasons scientists developed the concept of dark matter. Dark matter does not appear to absorb or emit ordinary light, making it invisible to conventional telescopes. Its presence is inferred primarily through gravitational effects. But even the dark matter picture continues to be investigated. Large astronomical surveys have improved our measurements of stellar positions and motions, providing researchers with increasingly detailed information about the structure and mass of the Milky Way. These observations help scientists refine estimates of how much matter our galaxy contains and how that matter is distributed. The mystery becomes even larger when astronomers study the universe on the greatest scales. There have been claims and studies involving unusual large-scale motions of galaxy clusters, sometimes described using terms such as dark flow. Some of these ideas remain debated, and they demonstrate how difficult it can be to separate genuine cosmic structure from observational limitations. What we do know is astonishing. The ordinary matter that forms stars, planets, gas, dust, and living organisms represents only a small fraction of the universe's total energy and matter budget. The standard cosmological model attributes roughly 5% to ordinary matter, around 27% to dark matter, and most of the remainder to dark energy. Yet we still do not fully understand the fundamental nature of either dark matter or dark energy. That means most of the cosmic inventory remains mysterious. And the mysteries continue when we look toward the distant universe. Because light requires time to travel, powerful telescopes allow us to observe the universe as it existed billions of years ago. As space expands, the wavelengths of traveling light become stretched toward longer wavelengths. This phenomenon, known as cosmological redshift, allows astronomers to estimate how far away and how ancient distant objects may be. Infrared observatories have become especially important because some of the earliest galaxies are extremely faint and their ancient light has shifted toward infrared wavelengths. When astronomers began examining the young universe in greater detail, they encountered another surprise. Some early galaxies appear more developed, massive, or chemically complex than certain theoretical models had expected. This does not automatically mean that modern cosmology has failed. Instead, it gives scientists something valuable, a problem to investigate. Perhaps galaxies form stars more efficiently than expected. Perhaps massive black holes grew unusually quickly. Perhaps our models of early galaxy formation need refinement. Science advances precisely through these moments. Every unexpected observation becomes another test of our understanding. And as telescopes continue looking deeper into cosmic history, the universe keeps presenting questions that are larger than the answers we already have. The farther we look, the less simple reality appears. And the next mystery may be waiting not billions of light years away, but inside a distant planet's atmosphere. The discovery of planets beyond our solar system has completely changed the way humanity thinks about other worlds. Only a few decades ago, confirmed exoplanets were still unknown. Today, thousands have been identified, revealing an astonishing variety of planetary systems. Some worlds orbit incredibly close to their stars. Others are enormous gas giants. Some are smaller and potentially rocky. And a number of planets orbit within regions where temperatures could, under suitable atmospheric conditions, allow liquid water to exist. But being located in a so-called habitable zone does not guarantee that a planet is actually habitable. Its atmosphere, chemistry, radiation environment, geological activity, and relationship with its host star all matter. Modern telescopes can begin investigating some of these characteristics. One powerful technique is transmission spectroscopy. When a planet passes in front of its star, a tiny portion of the starlight travels through the planet's atmosphere. Different molecules absorb different wavelengths. By analyzing those missing wavelengths, astronomers can search for chemical signatures within the atmosphere. This method has already revealed atmospheric components on distant exoplanets. For example, observations of WASP 96b have provided evidence of water vapor in its atmosphere, demonstrating how much information can be extracted from the light of a planet more than 1,000 light-years away. But detecting water vapor is not the same thing as detecting life. That distinction is extremely important. Water is chemically interesting, but it can exist in environments where life is impossible. The same principle applies to many other molecules. A potential biosignature must be interpreted within the complete planetary environment. Scientists must consider whether geological or atmospheric processes could create the same signal without biology. Our own solar system provides a powerful reminder of how strange planetary chemistry can become. Saturn's moon Titan, for example, possesses a thick nitrogen-rich atmosphere and a surface environment involving methane and hydrocarbons. Its chemistry demonstrates that complex organic processes can occur under conditions dramatically different from those on Earth. These discoveries have strengthened the scientific motivation to search for life elsewhere. But they also introduce one of astronomy's oldest questions. If the universe contains so many stars and planets, why have we not yet found clear evidence of another technological civilization? This question is often associated with the Fermi paradox. There are many possible explanations. Perhaps intelligent life is rare. Perhaps civilizations do not survive long enough to communicate across interstellar distances. Perhaps technological societies use communication methods we have not detected. Or perhaps the distances between civilizations are simply too enormous. There are also ideas involving multiple universes, cosmic inflation, and different physical conditions beyond our observable region. However, these remain theoretical possibilities rather than established explanations for the absence of extraterrestrial contact. The larger lesson is that scientific knowledge is never truly finished. When observations disagree with predictions, researchers do not simply erase the observations. They investigate. One example is the continuing discussion surrounding the Hubble tension, the difference between estimates of the universe's expansion rate derived from different observational methods. Measurements based on the early universe and measurements based on the relatively nearby universe have not always produced exactly the same value. The discrepancy has encouraged scientists to investigate whether unknown systematic effects, incomplete models, or perhaps new physics could be involved. Various theoretical possibilities have been proposed, including modifications to our understanding of gravity, dark matter, or dark energy. But none should be treated as a confirmed solution until evidence supports it. That is what makes astronomy so fascinating. The universe does not become easier to understand as our instruments improve. It becomes more detailed, more complicated, and, in many ways, more mysterious. From the first recognition that galaxies exist beyond the Milky Way to modern observations of ancient galaxies and distant exoplanets, every technological breakthrough has expanded the boundaries of human knowledge. We can now reconstruct events that happened billions of years before Earth existed. We can measure the movement of stars. We can study the chemistry of worlds orbiting distant suns. We can observe ancient galaxies whose light began traveling toward us when the universe was still young. And yet, despite all of this progress, enormous questions remain unanswered. What exactly is dark matter? What is dark energy? How did the first galaxies assemble so quickly? How common is life? Could intelligence exist somewhere beyond Earth? And are the laws of physics we observe here truly universal? Humanity occupies only a tiny moment in cosmic history. But within that brief moment, we have developed the ability to look across billions of years of space and time. That may be the most extraordinary discovery of all. The universe is not becoming smaller as we learn more about it. It is becoming deeper. Every answer opens another question. Every observation reveals another mystery. And the journey toward understanding reality has only just begun. 6.